Start our next session, which would be concentrated on uh, X-ray free electron laser research. And I would like to invite next speaker, which would speak about Attosecond X-ray free electron lasers, and it will be Professor Vitaliy Goryashko from double affiliation from Sakla, Japan, free electron laser, and from Uppsala University.
Yes. Yes. Hello, everyone, and konnichiwa from Japan. All right, let me share the slides. Mhm. So do you see full screen?
Yes, of course. Perfect.
Let's see if laser pointer works well. And also the laser pointer works, right? Is it all right?
Yes, yes.
Yep. Good. So let us set the stage. We will be talking today about attosecond physics. So let us understand what are the scales that we're interested in. Let's consider a simple hydrogen atom in the ground state. Just one electron orbiting around the proton. The characteristic energy scale is 10 atom volts, and the spatial scale is 1 angstrom. It takes 150 attoseconds for the electron to make one turn around the nucleus in the quasi-classical approximation. The Heisenberg uncertainty limits accessible pulse durations for a given energy. So for energy of 0.33 electron volts, the shortest possible duration is 0.3. For an energy of 1 electron volt, the shortest possible duration is 0.33 femtoseconds. So let's see where we can find such time scales. Not in nanostructures, because the characteristic energy interaction is on the sub-electron volt. In molecules, valence electrons usually have energies few of tens of electron volts, still not enough for attosecond physics. But if we look at the core electrons in atoms, the interaction energy is typically much larger than 10 electron volts. And then the dynamics of core electrons happens on the attosecond time scale. That's where we need this resolution and this precision. Let's see what kind of science drivers motivate this development of attosecond physics. There are different processes which happens on the femtosecond or even sub-femtosecond time scale. This plot shows the time scale in femtoseconds, and the horizontal scale shows the energy. That is the characteristic interaction energy. In the low energy region of this plot, we find such processes as charge migration, charge screening, photoionization dynamics. All these processes are very important for understanding how the molecule functions. I will give an example on the next slide. If we are talking about high photon energies, then the interest is in Auger decay, Coulomb explosion, and different kind of coherences. Let's take a look at the charge migration. So what is that? Imagine we have a molecule and we ionize one side of the molecule and remove one electron. That gives rise to a hole. What happens with the hole? How does it move? And how does it migrate within the molecule? So this question is important for understanding the energy transfer on the molecular level. Here on the right, you can see an example. This is an experimental study by Ferenc Krauss, who got the Nobel Prize in 2023. In the experimental study, they used a molecule of iodoacetylene, and the iodine side of the molecule was ionized. So it's quickly ionized. One electron is removed, and we see that after half a second, and so this this shaded area schematically shows the hole which appeared after the ionization. After half a second later, the hole delocalized over the molecule, and we see that 1 second later, the hole is localized on the acetylene side. 1 second later, the hole is moved back to the iodine side. So the whole process takes around 2 femtoseconds. So this study was done actually using an HEG source. So we see that indeed the whole dynamics happens on the femtosecond time scale, and in order to resolve this motion, we need attosecond precision. Let's see what kind of sources are available to study attosecond dynamics. The plot on the left shows accessible pulse progress in the generation of shortest possible pulses as a function of time. So the first lasers, they were continuous. But shortly after the discovery of the laser, the technique of mode clocking was developed. So this technique of mode clocking made possible generation shorter pulses and down to the regime of some femtoseconds. So the picosecond barrier was broken in the 70s, and the generation of pulses as short as 5 femtoseconds were demonstrated around the 80s. However, for around 20 years, the progress stayed on a plateau. So there was really no future progress in shortening the pulse duration. However, during this period, two important techniques were developed: short pulse amplification in lasers and high harmonic generation gases. So the technique of short pulse amplification received the Nobel Prize, if I remember correctly, in 2018 or maybe 19. And the technique of high harmonic generation gas received the Nobel Prize in 2023. So these are two very important discoveries in physics which made possible accessing the attosecond time scale. At the same time, we see that in recent years, the progress in the second pulse generation started to slow down. However, using advanced concepts based on duet radiation, it's possible to further reduce the pulse duration, and there are ideas how to generate pulses as short as few attoseconds, or even on the sub-attosecond pulse region. Here is another visualization of the progress in the short pulse generation. So on the left, you see the pulse energy as a function of the pulse duration. Most of the results with ultra-short pulses were demonstrated using HEG sources. So that is the current frontier of science. First FELs, first fractal lasers, made possible generation of femtosecond pulses with very high energies on the millijoule scale. The first generation of attosecond pulses with FELs was demonstrated at LCLS around 2017, and they reached pulse durations as short as around 250 attoseconds. At the same time, using new ideas based on duet radiation, it's possible to reach the terra incognita of ultra-fast world and generate pulses as short as 10 attoseconds or even shorter. An X-ray field is a unique instrument. Not many X-ray fields exist around the world. One example of the first field is FLASH in Germany, in Hamburg. That was a 1 GeV machine, which at that time was 300 meters long, and now it's a small field, 300 meters. Nowadays, it's nothing compared to modern field monsters. And that was in VUV X-ray field. In 2009, LCLS started its operation, shortly after followed by the operation of Sakurai field in Japan. So LCLS that was demonstrated for the first time generation of femtosecond X-ray pulses. But the machine was huge at the time, 1.6 kilometers. At Sakura, they used several innovative ideas and made the laser just 600 meters short. After that, almost like a decade later, a bunch of other EFLs came to operation. Polyfield in Korea, then Swiss EFL in Switzerland, and the European EFL. So my colleague, Svetozar, he will talk in detail about the European EFL and how they generate attosecond pulses there. But that is a monster machine, 3.6 kilometers long, and accelerates the beam up to 20 GeV. There are also ideas how to make more compact EFLs, like the idea proposed a few years by the European Consortium of Compact Light, that would be just 400 meters with more affordable price. Meanwhile, in China, they're building another monster, the Shine facility, which will be 3 kilometers long based on superconducting linac. And in the States, now they're upgrading LCLS2. All right, there are really many ideas have been put forward how to generate attosecond pulses. So here you see lots of ideas. I will not describe in detail these ideas, but I will just quickly go through. At least you will see what happens in the world of attosecond X-ray fields. Because these methods, they are very different and serve different user needs. And sometimes it doesn't really make sense to directly compare different methods, because it's like a racing car versus a truck. They serve different functions, different purposes. All methods of generating ultra-short pulses and fields, one can divide into two broad areas. One bunch of methods is based on the field process itself, and another group of methods is based on preparing a very short electron bunch. So the first group makes use of single SASE or single SASE spike field radiation, or pulse self-compression in the super irradiant regime, tapered field, mode locking, and other advanced concepts. Or the second group of methods, it relies on making a very short electron bunch, such that when it goes through an undulator, it emits coherent radiation, just one very short SASE spike. I'm afraid that most of you are not really familiar with the field physics, but nevertheless, let me just give you a quick outline what happens and what kind of developments has been demonstrated and what is possible to achieve nowadays. First of all, I need to mention that in the field, the pulse is not coherent. So the radiation pulse, it's the power, it's a function of time. The radiation pulse consists of a series of shorter radiation pulses. That is because the field starts from short noise. It's not really a laser. It's not really coherent in terms of temporal properties. If we can make the electron bunch very short, then it will emit just only one radiation pulse, and this radiation pulse called SASE spike. So for soft X-ray fields, one radiation spike or one radiation pulse is typically between 0.5 and 1.5 femtoseconds. For hot X-rays, this one radiation spike is shorter, typically 0.15 to 0.4 femtoseconds. So the challenge is to prepare a short electron bunch. All right, how we can do that? The simplest idea is that an electron bunch from an accelerator forced to travel a curvilinear path, and on this path, one inserts a screen with a small wedge-like opening. So that is the method called slotted foil. So most of the electron bunch is destroyed, and only one short part of the electron bunch is good and able to produce radiation in an undulator. So in this way, it was for the first time demonstrated LCLS. They showed, so they produced an electron bunch as short as 1 femtosecond and demonstrated lasing at 5.6 keV. And in this way, 65% of shots, 65% of pulses were just single spike. with an average energy of 5 microjoules. And you see, with the duration as short as 400 attoseconds. Later, again at SLAC, they demonstrated the method of nonlinear compression, which allows producing very short atom bunches just by squeezing them in the original phase space. In this way, they demonstrated lasing at 5, or let's say 5 and 9 keV, and with the pulse duration as short as 230 attoseconds. So it's really the attosecond time regime. That is more advanced concept. It's based on the fact that during the nonlinear process, the pulse duration naturally reduces. So the radiation pulse forms some sort of soliton, and this soliton squeezes as the pulse is amplified during the field. So that is a visualization. That is a simulation, which was also tested experimentally. So this white line shows the width of the radiation pulse. And we see that after some point, the radiation pulse started to reduce longitudinally. This effect is difficult to use, but it's demonstrated, and actually it works. Maybe in the future it will be implemented somewhere. So that is an advanced scheme from Takashi Tanaka from Sakurai field, in which he proposed to use to select one part of the atom bunch, modulate the certain bunch using external laser to produce short spikes of the electron current, and when this electron current goes through an undulator, it generates a series of radiation pulses, and then the pulse length decreases down to the level of 50 attoseconds in simulations and reaches a very high peak power. But this method actually is quite complicated because it requires a very precise control between this radiation, between these micro bunches of electrons and radiation pulses. So therefore, there was a number of techniques which are much simpler and use different variations of the slotted foil. So what I already briefly mentioned, this is in this way the quality. So some parts of the electron bunch are removed, and only short pieces or short microbunches allowed to generate in an undulator. So what we see here, that is the distribution of that's the electron distribution, and only these short regions are allowed to produce radiation in undulator. And in this way, they demonstrated, I think that was already an experimental study, they demonstrated generation of 200 attosecond pulses with an energy up to 200 microjoules. The next development was also at the Swiss FEL 2015. They proposed to use different parts of the electron bunch. So what they proposed, they, instead of sending the electron beam directly through the undulator, they gave a kick to the electron beam, so it starts to oscillate transversely as it propagates through the undulator. So only a small group of electrons actually is lasing inside the undulator, because the rest are coming in the wrong phase. So in this way, they demonstrated lasing of 2 femtosecond pulses at an energy 670 eV. And around 10% of spikes were, and 10% of pulses were single spike. That is, now we're coming to the technique developed at DESY. That was Evgeny Saldin and his co-workers, which proposed a method that is quite an advanced method. They use an external laser pulse to modulate the electron beam in an energy modulator, and by adjusting the phase between the electron beam and the Pandramoti wave in the undulator, they generate also very short radiation pulses down to the level of like 100 attoseconds. Maybe Svetozar will give a little bit more details about this technique. One can also generate CP-stable pulses in a very simple configuration if we just use one modulator and modulate the atom density using an external laser. Then this modulated atom density will radiate a Doppler upshifted pulse at high frequency in the device called radiator. So here that is a simulation showing how a microbunched beam emits radiation just propagating through magnet containing 1.5 periods. So that is kind of simple scheme which allows for generation of carrier envelope phase stable pulses. I think that's probably a little bit too advanced. I will skip this part because I want to give you to add some words about attosecond diagnostics. So I will skip these advanced schemes. So let's talk how can we actually measure pulses as short as some attoseconds. So this method is called attosecond angular tracking. It works as follows. An X-ray pulse, so that is an X-ray pulse from a field. It goes through a gas of some molecules. X-ray photons, they can ionize the molecules and release electrons. Then, if we also superimpose an external infrared pulse on top of the X-ray pulse, we can force these released electrons to be modulated in momentum, and then by studying this momentum configuration, we can find the time moment when they were generated. So yeah, this is a little bit different visualization. So an electron bunch, let's say, imagine that we have some electrons which are propagating forward, and then also comes an infrared pulse from the back. And this infrared pulse will modulate electrons and send them in different directions depending on the relative phase between the electrons and the wave. So in this way, we can measure extremely short pulses down to resolution of 20 attoseconds. So that is the technique of angular tracking. And that is an experimental demonstration at LCLS at Stanford. So an X-ray pulse goes through a gas of molecules, ionizes these molecules, and then photo-emitted electrons, they measure it using 16 time-of-flight spectrometers. So in this way, they were able to reconstruct spectra and measure very short pulses. Here is a typical demonstration. So the kinetic energy of emitted electrons, their phase, and then the reconstructed pulse duration of the X-ray pulse. So the reconstructed time duration is in the order of some 30 seconds. One can also generate and reconstruct double attosecond pulses. So here what we see is the delay between double attosecond pulses as a function of time. Later on, they developed a little bit modified technique in which, so I will not go into details of the whole scheme, in which electron X-ray pulse ionizes molecules inside a velocity mapping spectrometer, and electrons are mapped on a screen by using an allostatic potential of the spectrometer. So in this way, one can get the spectrum the distribution of photo-emitted electrons in one shot. And that allows reconstructing X-ray pulses. And we see here some examples of reconstructed X-ray pulses. All right, so that was a lot of information, and probably, not probably, for sure, most of this information was highly specialized. But I wanted to show you a little bit, give you a little bit of taste of very, very modern developments in attosecond science, what really happens in X-ray fields nowadays. So I will conclude with a slide. So the development of lasers in the 60s made possible modern communication, in particular based on fiber optics. The development of synchrotrons in the 70s made possible crystallography. And nowadays, scientists made a huge database of different molecules which allow for crystallization. The advent of retinal lasers made possible single molecule imaging. Further, the development of high Helmholtz generation in gas made possible seeing observation of light waves, for example. And in 2016-17, a new era started in attosecond physics by using X-ray fields. And maybe one day we'll be able to see coupled electron-nuclear dynamics using X-ray fields. So fields or the X-ray field is a unique transformational instrument which allows access to time scales and spatial scales not accessible by any other instrument. All right, so I conclude with that. And thank you for your attention. And I think I have a couple of minutes for questions.
Thank you very much for kind of very straightforward and interesting talk on free electron laser development. So I'm asking for questions from, is there any question in the public?
I just have a comment. I liked your plot of FEL development as kilometers per year.
Kilometers per year, yeah. Exactly.
But probably at some point we would have tabletop FELs and then it will decrease.
We have been working on that. Still hard. It's still hard with tabletop fields.
We should talk about microjoules per kilometer then.
Yeah, exactly.
And so basically, if I understand correctly, you are currently working on the at SACLA and
Yep.
facility, and what is the current shortest pulse duration which you succeed to reach?
At SACLA?
Yes.
At SACLA, actually, it's not, it's still, SACLA still operates in the femtosecond regime. It's
Okay.
around 5-6 femtoseconds.
Okay.
Surprisingly, Japanese users are not so interested in attosecond pulses. So there is not so much push from users here.
Okay. And anyway, it's very exciting, and I guess we should move to the next talk, which will be deeply related to previous one, and it will be performed by